Today we're looking at eigenvalues and eigenvectors. Hopefully by the end of this we can compute the eigenvalues for 2x2 matrices and 3x3 matrices, solve the characteristic equation, and compute eigenvectors of symmetric matrices. Cool. To understand what eigenvalues and eigenvectors are, we must know that matrices transform vectors in a certain vector space. So when we do a matrix times a vector, it is going to transform that vector. For example, it could rotate it 90 degrees, it could stretch it or enlarge it. And when that happens, most vectors change in both magnitude and direction. But eigenvectors keep the same direction and only their length changes. So if I had the matrix A, B, C, D and multiplied it by the vector xy, I'm still going to get that vector xy, but because the magnitude of this vector has changed, we can represent that magnitude using lambda. So xy would be our eigenvector and lambda is our eigenvalue. So if we had some three-dimensional space, if this is our vector xy, under this transformation, it might elongate. So this is x, this could be lambda x, where x is a vector. So looking at the more formal definition, an eigenvector of a matrix A is a non-zero column vector x which satisfies the equation the matrix A multiplied by the vector x is equal to lambda x. So this is exactly what I wrote over here, where lambda is a scalar. Then the value of this scalar lambda is the eigenvalue of that matrix A corresponding to the eigenvector x. This equation, which is the determinant of A minus lambda I, which is equal to 0, is called the characteristic equation of A. The solutions to this characteristic equation are the eigenvalues of A. If I now make up some sort of random matrix, so if we had this 2x2 matrix A, which is 3, 4, minus 2, 9, if we work out the eigenvalues of this matrix, we would have to use that characteristic equation, which was that A minus lambda I and equal that to 0. So if we write this matrix, we get 3 minus lambda, 4 minus 2, 9 minus lambda. And that is simply because we are doing 3, 4 minus 2, 9 minus lambda 1, 0, 0, 1, which we can write as lambda 0, 0, lambda is equal to 0. So we now need to work out the determinant of this matrix, and that would be 3 minus lambda multiplied by 9 minus lambda minus 8. So these two times together minus these two times together. If we now expand this out, we get 27 minus 12 lambda plus lambda squared plus 8 is equal to 0. So lambda squared minus 12 lambda plus 35 is equal to 0. Cool. So now we get this quadratic. Our first solution to this quadratic is 7. Our second solution is 5. So these two would be our two eigenvalues. A quick way to get to this final quadratic equation is to use this rule. So for any 2x2 matrix, to work out this quadratic characteristic equation, it will be lambda squared minus the trace of that matrix, lambda, plus the determinant of that matrix A, and that's equal to 0. Just to see if this holds true, we will use it right now. So lambda squared minus the trace is just the sum of the two elements in the leading diagonal, so 3 plus 9, which is 12. So minus 12 lambda plus the determinant, which is 3 times 9, which is 27, minus 4 times minus 2, which is minus 8. So we get lambda squared minus 12 lambda plus 35, which is the same thing over here. So that's just a quick way to get to this step without having to do all of this working out. Now that we have the eigenvalues, if we had to work out the eigenvector, we would use this equation but now sub in our known values of lambda, or our known eigenvalues. So 3, 4 minus 2, 9 multiplied by the vector xy is equal to 7 lots of the vector xy. So what this is saying is 3x plus 4y is equal to 7x. So 4y is equal to 4x. So x is equal to y. So that means a possible eigenvector could be 1, 1. And to work out an eigenvector for the eigenvalue 5, we will just now sub in 5 into here. And so to get 3x plus 4y is equal to 5x. So 4y is equal to 2x. So y is equal to a half x. So one possible eigenvector would be 1 and then a half. Cool. Hopefully that makes sense. Now, if we look at a 3 by 3 matrix, let's say we had the matrix A, which is equal to 2, 1, minus 3, 0, 2, 1, 0, minus 4, minus 3. Now again, using the characteristic equation, we need to find the determinant of the matrix 2 minus lambda, 1 minus 3, 0, 2 minus lambda, 1, 0, minus 4, minus 3, minus lambda. In order to find the determinant of this matrix, I'm going to use the second row and then work out the determinants of the minor matrix. So if I use the second row, I get minus 0, and then the minor matrix is 1, minus 3, minus 4, minus 3, minus lambda. Then I get plus 2 minus lambda, and the minor matrix is 2 minus lambda, minus 3, 0, minus 3, minus lambda. And then minus 1, 2 minus lambda, 1, 0, minus 4 is going to equal 0. So of course we don't need to compute this one, and we can skip over straight to this, and we get 2 minus lambda, 2 minus lambda, minus 3 minus lambda, and then minus 1 brackets minus 4, 2 minus lambda is equal to 0. I'm just going to factorize out 2 minus lambda, so then I am left with 2 minus lambda minus 3 minus lambda plus 4 is equal to 0. And so we get this, and then if I collect all the like terms, we get lambda squared plus lambda minus 2 is equal to 0. So we know that our first eigenvalue is lambda is equal to 2. Our second eigenvalue is 1, and then our third eigenvalue is minus 2. If we are now going to work out the corresponding eigenvectors, let's start with lambda 1, which is 2. Essentially, we're doing the matrix A multiplied by x, y, z, and that is equal to 2 lots of x, y, z. If I multiply the first row by x, y, z, I get 2x plus y minus 3z is equal to 2x. If I do the second row, we get 2y plus z is equal to 2y, and then the last row is 4y minus 3z is equal to 2z. If we look at this equation, we can tell that z must be equal to 0 to fulfill this equation. So now that we know z is equal to 0, if we substitute that into here, we get 2x plus y is equal to 2x. So that means y must also be equal to 0. And then over here, when we substitute our values of y and z, we just get 0 is equal to 0. So we get the eigenvector of 0, 0. And then if we look at x can pretty much be any value. So the simplest value to take is just 1. So for our first eigenvalue, we get the eigenvector 1, 0, 0. If we now do a similar thing with 1, we get 2x plus y minus 3z is equal to x. 2y plus z is equal to y. If we look at this, we're going to get y is equal to minus z. So if we let z is equal to 1, then we get y is equal to 1. If we substitute this into the first equation, we're going to get 2x plus 1 minus 3 is equal to x. So x is equal to, so if we let z is equal to 1, we get y is equal to minus 1. If we substitute this into the first equation, we get 2x minus 1 minus 3 is equal to x. So x is equal to 4. So our eigenvector for this is 4 minus 1, 1. And finally, if we do minus 2, we get minus 2x and minus 2y, and then minus 4y minus 3z is equal to minus 2z. If we look at this equation, we get 4y is equal to minus z. So if we let y is equal to 1, we get z is equal to minus 4. And like before, if we substitute that into the first equation, we get 4x is equal to minus 1 minus 12, which gives us x is equal to minus 13 over 4. So this one becomes minus 13 over 4, comma 1, comma minus 4. Cool. Just like before, if you want to skip these steps and go straight to our now cubic characteristic equation, you could use the rule. So if I write this like before, for any 3 by 3 matrix this time, to calculate the characteristic equation, we get lambda squared minus the trace of the matrix A, lambda plus A11 plus A22 plus A33, lambda minus the determinant of the matrix A, and that's equal to 0. This is not what you think it is, but we'll look at the whole equation first. This should be cubed. So we get lambda cubed minus the trace, which is just all the elements in the leading diagonal added together, which is just 1. So we get lambda cubed minus lambda squared, Now, this is just the determinants of the matrix of minors for the element A11. So this is A11, we would get rid of its column, get rid of its row, work out the determinant of this matrix, which is minus 2, and then we're adding that to the matrix of minor we get when we get rid of A22, which is this term here. We get rid of its row, we get rid of its column, and we just get minus 6. And then finally, we look at A33, we get rid of its column, get rid of its row, calculate the determinant, which is just 4. Then we have to work out the determinant of the whole matrix, which if I use the diagonal method, will just be minus 12 plus 8. So we get lambda cubed minus lambda squared minus 4 lambda minus 4, which is plus 4, is equal to 0. So our eigenvalues are minus 2, 2, and 1, the same that we got before. So this is just another approach, and maybe a quicker approach to working out the values for a 3x3 matrix. Cool. Now, looking at the eigenvalues of a symmetric matrix, we should probably first understand what a symmetric matrix is. A matrix is symmetric if A, the matrix A, is equal to the transpose of that matrix A. So let's say we had 5, 2, 7, 4. If we now transpose this matrix, we would get 5, 7, 2, 4. So these columns now become rows. This is obviously not the same matrix, so these matrices are not symmetric. If we instead have the matrix 2, 7, 7, 5, when these columns become rows, we get 2, 7, 7, 5, and that is the same matrix. So these two matrices are symmetric. Cool. An example of a symmetric matrix is a Hessian. When we calculate the Hessian, these two are always the same, hence a Hessian is always symmetric. Why that's important is that for a symmetric matrix, the eigenvalues are always real. The eigenvectors are orthonormal, and so they form an orthonormal basis, and this links to spectral decomposition, which we will look at next time. So if we use this matrix 2, 7, 7, 5, and if we use our rule of lambda squared minus the trace of the matrix A, lambda plus the determinant of that matrix, we get lambda squared minus 7 lambda plus minus 39, and we get two eigenvalues, which is 10.65 and minus 3.658, which are both real. If I have another matrix, which is 3, 1, 1, 3, if I work out the eigenvalues for this using our characteristic equation is lambda squared minus 6 lambda plus 7 is equal to 0. Plus 8. We get lambda is equal to 4 and lambda is equal to 2. So this can be our first eigenvalue and this can be our second eigenvalue. If we now work out the corresponding eigenvectors, we get 3x plus y is equal to 4x. So y is equal to x. So our eigenvector for lambda is equal to 4 could be 1, 1. If we do the same thing for lambda is equal to 2, we get 3x plus y is equal to 2x. So y is equal to minus x. So we can get minus 1, 1 as an eigenvector when our eigenvalue is 2. If we now dot these two, we get minus 1 plus 1, which is 0. When the dot product is 0, it means that the two vectors are orthonormal. Cool. Another thing that we can say about these vectors is that they are also linearly independent. That is because if we have some value, let's call it alpha, multiplied by our vector 1, 1, plus alpha 2 multiplied by our vector minus 1, 1, and if we equate this to 0, to test if these two vectors are linearly independent, it means that the only solution which can exist should be when alpha 1 and 2 are equal to 0. So if we do that, we get alpha 1 minus alpha 2 is equal to 0, and alpha 1 plus alpha 2 is equal to 0. So that's just me expanding or timesing the alphas by the vectors. If I now add these two equations, we get 2 alpha 1 is equal to 0. So alpha 1 must be equal to 0. And then if we sub this back into here, we get alpha 2 is equal to 0. Hence, because the only solutions exist to this equation, when alpha 1 is equal to 0 and alpha 2 is equal to 0, these two are linearly independent. That is always the case. The eigenvectors for a symmetric matrix will always be linearly independent. If you're unsure on what this is, check out the video on vector spaces and linear independence. Cool. So hopefully we know how to compute the eigenvalues of 2x2 and 3x3 matrices. We know how to solve the characteristic equation, and we can compute the eigenvectors of symmetric matrices. Hopefully this was useful. Make sure to use the link in the description to buy me a coffee. That would be much, much appreciated. And also do subscribe now, this instant. Thank you.